circuits. So that shows with the yellow dot, that is mini computers, mainframe plus mini computers. So we had about 10 million plus units integration. Then as time goes on, then in 90s, mid 90s, it was dominated by personal computers, PC, and then so it was 100 million plus units integration. So that is shown by this green circle. And then as we continue in 2000 and beyond, so we have this blue circle that shows the desktop and internet. All these things are coming up, and then we have about 1 billion plus units integration. And then in this decade, it started early 2010, so that we have mobile internet, 10 billion plus units integration. So we see that increasing integration, and all these things are possible because of transistor scaling. So transistor scaling, that actually accelerated the high performance low cost transistors due to scaling, and then that actually excited people, all investors, to invest, and then market growth. So all these things are moving in a cycle, in a circle. So that is all dominated by transistor scaling. And as a result of that evolution of products, which are smart devices like iPad, iPhone, tablet, and all other things, then we have PDA tools, then automotive electronics, GPS, APS, then autonomous vehicle, then mobile videos, home entertainment, games, wireless home, that is smart homes and appliances, and then voice, that is Alexa, Google, Siri, and all sorts of things. And then explosion of internet and digital society. So next page we go. Show that this is on impact of silicon devices on society. You see that all these things, business, main theme is business. So business is connected to transport, to energy, then education, home, and then cities, smart cities. So all these things are interconnected. So we have a network of networks are connected to the business and all important items, and then that actually created Internet of Things or Internet of Everything. So that is on the right hand view of a plot. It shows that we have people. So process in the middle. Then we have people, data, things. So and it is connected to home, mobile, or environment, and then business. So we have people-to-people connection, the people-to-people communication. Then we have people to machine, that is things, people-to-machine communication, that is people-to-machine, and then and then machine-to-machine, that means data and things, their communications, all sorts of things that started, which actually created, next page, which created integrated smart environment and integrated ecosystem. So this is what it shows, that we have on the left-hand side, we have the smart homes. That home is connected to networking, then smart energy, then smart meters, then computing, media, and all sorts of things are smart homes connected. Then we have autonomous vehicles. So vehicles, all the accessories for the vehicle, which is all the all IC chips, and then medical, which is also connected to the net, and then industry, so industry or business, then aviation, and all sorts of things, and all can be accessed by this mobile phone, that is smartphones. So smartphones, just sitting on the smartphones, we can connect to any of these things. So this is a smart environments and integrated ecosystem. So all these are all contributions of this silicon technology. So next page we show Next page, we shows a few IoT enabling products. This is just for illustrations only. There are hundreds of products. So what about, it says that what are the IC chips? Then what are the IC chips that is used for automobile? Then automotive, then connected homes, that is smart homes, then industrial applications, machine to machine, then we have medical, then mobile devices, smart energy, and wearables. So these are all contributions of IC chips. Though we talk about more on Facebook, Google, which we don't see, but heart of these are all these left-hand side, the IC chips column. That is for automotive, what are the things that we need? Then for wearables, you have low noise amplifier. So these are all silicon technology, and then circuits and systems, all these things. So these are few examples. There are a lot of examples, 100 plus. So we can go all the products that is coming out from the IC fab, and then the systems, circuits and systems design. So on the next page, on next slides, what we show is that all these things are possible by metal oxide semiconductor field effect transistors, which is MOSFETs. These have been the driver of digital age for last few decades, providing core capabilities for IoT infrastructure, sensing, connectivity, computing, that is big data, and then enabling smart environments and integrated ecosystems. So this is a typical advanced MOS device. So all this device has, everybody is familiar with. It is characterized by gate length, gate width, then source drain SDE is source drain extension, then DSD is deep source drain junction, and then excuse me, and then it is isolated from the neighboring devices by oxide STI, which is shallow trench isolation. So this is basically, this is the device that is changing the world from late 1970s to until now. So next page. On next page we show that is we are finished that thing. Then we see that these silicon devices, what are the challenges that we have with these silicon devices that is facing right now to continue to the growth of these digital media, of the products for digital media. So on next page we show so the challenges. First challenge is, if we see these plots, IDS, VGS graph. So what we see, this is plotted as a function of gate length. So bottom curve, which is blue, that shows gate length of 250 nanometers or 0.25 micron, and then go up to 30 nanometer. So what we notice that our this is taking at VDS is equal to 0.9 volts. So this is actually a saturation region. So at bottom curve shows that I off is about 10 to the power minus 10. Then next green curve, which is a gate length of 100 nanometer. So offset leakage current, which is about 3 times 10 to the power 9. So it is offset leakage current, leakage current is increasing and becoming about more than 10 to the power 5, 10 to the power minus 5 amps per micron for devices with 30 nanometer channel length. So what we see that all this threshold voltage, then subthreshold slope, this slope is given subthreshold slope, in the leakage current, all are functions of channel length. That is gate length sensitive device parameters, which is threshold voltage, subthreshold slope, leakage current, and then so that means that we have degradation of all these parameters, ETH, subthreshold slope, and then offset leakage current as we scale down the devices. To mitigate these scaling constraints, what we have to do is need higher bit threshold voltage. That means so that leakage current we can control. So it means that we have to use more doping, and then higher threshold voltage means we have to increase the supply voltage, which is VDD. And in case doping, which means that this is another problem, which is coming to the next, is so this increases design cost. Supply voltage, that means we will lose power consumption. So on the next page, we show, let's continue on the next page. So here we see that MOSFETs, so under those circumstances, that means increasing channel length dependent parameters, so MOSFETs cannot meet the design challenges. So design, what we need is low threshold voltage for design, low offset leakage current, then smaller subthreshold slope, that means it should be swing should be very fast, and then less variation of subthreshold slope. That we see that conventional MOSFETs cannot meet the design requirements for integrated VLSI circuits and systems. So on next page we show.
Yeah, I request all of you to please mute yourself. A lot of background noise is coming.
So this page basically continue on the same theme. That is, this page shows that why this offset leakage current. That means gate is losing control when a smaller devices. Gate is losing control because of the coupling between drain and the channel. That is, the source and drain are in close proximity. So as a result, this CDSC, which is drain to channel coupling capacitor, that becomes dominant. So even sometimes it is comparable to gate oxide. So that means gate is losing control. And then sometimes it could be higher than gate oxide. So as a result, gate loses control, and then drain, because of this drain control, directly we have higher leakage current. As we can see for 30 nanometer device, this is basically a kind of resistors. That is, we don't need any more gate voltage. Just using drain voltage, we can turn on the transistor. So this is just a resistor. So the next page. Next slide. That's what it shows. That is drain. That is gate cannot control the leakage path below the surface. That means subsurface leakage. So subsurface leakage is cannot control by gate. So as a result, so this is leakage directly from the source to drain leakage, that which contributes to the offset leakage current. So what we need is silicon body. So to make gate control better of the channel, gate control of the channel better. So what we need is silicon body closer to the gate in suppressing the leakage currents in sub 32 nanometer devices. So on the next page. So next page, as we said, that to control gate, to increase the gate control, or to decrease the leakage current, we have to increase the channel doping concentration. So there comes another problem, which is process variability, which is a major scaling challenge for the MOSFET devices. So on the these 3D plots, it shows that all these blue dots, they are basically dopant atoms. That could be coming from source drain as well as channel, because we can calculate how many dopant atoms we have if we take about 20 nanometer device, and then we calculate from the volume and then junction depth. You can see that for about 20 nanometer devices, the number of dopants could be impurities could be around less than 50. So those 50, so they are basically discrete, and so they can go anywhere instead of continuous, that we are used to know that doping profile is continuous. But here, because of this low number, this is discrete. So as a result, it causes random dopant fluctuations, or RDD, which is a random RDF or RDD. RDD is random discrete dopants. So these are discrete dopants. So that causes threshold voltage variation. In addition to that, because of lithographic process, we have oxide thickness variation, which is OTV. And then same with lithographic process, we have this rugged or rough edge. So that gives you line edge roughness, and then also line width roughness. So all these things come into play, which contributes to the variation of device performance. So next page shows the variations of device performance. This is if we plot statistically on current, the P channel on current in the vertical axis and the N channel on currents on the horizontal axis, then you can see these are the distributions of this on current distribution, whereas our design target has been these red dots at the center. So nominal data is red dot at the center, and our data is all over the place. So that puts a huge constraint for designers. So where to, how to design, and then where to put your guard band so that you can consider, or so that you don't lose too much of your design. So that is a huge challenge for the design engineers. And so this is the contributions of scaling or smaller devices. So next page. So after that, now to overcome the challenges, as you mentioned, that we can go ultra thin devices. So next page, we talk about those ultra thin body transistors. So first of all, that we have to eliminate leakage current. So if we have a very ultra thin body, so as shown on the left 2D structure, so we have the gate and this ultra thin body, and then if we can, this body is sufficiently thin enough, so what happens is subsurface leakage path, which is shown by this dotted curve, leakage path, it is cut off. So that we can cut off this leakage path as we thin down this T-silicon, as we thin it more and more, so all the leakage current basically in the silicon dioxide, which is box of buried oxide, and so in that way we can reduce the leakage current. And on the plots on the right hand side, it shows that as T-silicon is decreased, your leakage current off-state leakage current is decreasing. So this is ultra thin body SY devices, and also on the next page we can show that we can use gate control by using two gates on this ultra thin body. So we can use gate control. That means we can use a top gate, bottom gate. So top gate, what happened is in this case, on the subsurface leakage for the top gate will be taken care of by the bottom gate, and the subsurface leakage with reference to bottom gate will be taken care of, will be controlled by the top gate. So this way we can have undoped body, and at the same time increase the gate control. So this is a double gate MOSFETs. And then with the same idea that we can use a vertical thin channel, like with the two gates on the sidewalls, and then thin body. So this is basically the FinFET, which is source drain on the other side, and then fin is the same fin is inside, and this is oxide is showing on the both sides, and the top is basically masking oxide, so we can use that just to use only as a configuration. Right hand side, that is
Mute yourself. Hello, please mute yourself. We are seeing a lot of background noise. So except Dr. Saha, I request all of you to please mute yourself. Thank you. Yes, Dr. Saha, please proceed.
So, so this is the left hand side is a double gate MOSFET. So right hand side, that is a three-dimensional figure. So that also shows a double gate MOSFET, but it is a vertical structure. So this is the thin field effect transistor. So this thin body that is called the thin, and this is the FinFET structure. So on the next slide, we show. So next generation devices, ultra thin body transistors. So both FinFETs and UTB SOI, which is ultra thin body SOI, MOSFETs offer superior subthreshold swing because of the increased gate control. Then S and VTH less sensitive to L because of gate control, L and VDD. So no or reduced process variability, particularly dopant fluctuation, because we can have undoped body or very lightly doped body, so we can reduce dopant fluctuation or process variation, and no impurity scattering because of gate control, and at the same time we can do with the undoped or lightly doped channel. So and less surface scattering, lower effective electric field. So as a result, all these things increases mobility and high current, high performance. So thus provide higher on current, lower leakage, lower VDD and low power consumption, and then continuous scaling down to ultimate limit, which is predicted about 3 nanometer region. So next page we look at. So here it shows the double gate FinFET structure on the three-dimensional structure on the left-hand side, which shows all the parameters. T silicon is the thickness of the fin, and then source in front, and then drain at the back, and this gate, which is the red block that shows the gate, and then so this is on SOI substrate. So silicon and then oxide, which is the SOI substrate. And then if we take a two-dimensional cross section along X and X prime, X and X, so here we see that there's this 2D structure. So 2D structure over the gate, so that we can see there's gate on both sides. So this is kind of a double gate structure if we rotate that. So gate on both of our side walls on both sides of the body, and then we have a silicon substrate, and then box or oxide. So this is on SOI substrate. Next page. So next page, this shows this is bulk silicon, bulk FinFETs. So that is, we can prepare FinFET on the bulk substrate also. So this silicon substrate, and its process is little bit complicated because we have to have STI. So this is this oxide that shows that is basically silicon shallow trench isolation. Excuse me, to isolate the neighboring devices, and then again 2D cross section over the gate. So that shows this is the 2D structure for this 2D cross section of this 3D structure along the showing the fin in the middle and the gate on both side walls of the devices. So on the next page, so this shows both the devices. This is a triple gate. Previously we showed double gate. That means we had a thick cap oxide on the top. So now if we use same oxide thickness on the side walls as well as on the top, so we have a triple gate. So gate on the top and the gate on the side walls. So that's a triple gate. So there are other options also that people use, but I will talk about only double gate and triple gate. So this is the triple gate device. One is on SOI substrate on the left hand side and the bulk substrate on the right hand side. So on the next slide. So this shows the basic features of FinFETs. That is FinFET. What we have is gate channel, gate or channel length LG, and then fin height. Excuse me. Fin height as shows here is a H fin, and fin thickness T fin or T silicon as I shown before, and the gate oxide thickness T ox. Then if it is a double gate, we have a body doping NB, though it is very lightly doped, and then source and drain. So here it is showing opposite, that is source and drain. And then so FinFET also, if we're familiar with the MOSFET, so it has 3 modes of operations, that is accumulation, depletion, and inversion. So on the next page, the next page is just some calculations, that is what is the effective channel length. The effective channel length is Lg minus delta L. So delta L could be whatever the source drain penetration inside the oxide on fin, so on the sidewalls of the fin. So then so this is effective channel length, effective channel width, also same thing, and then only effective channel width and the width of the FinFET. So if it is a single tri-gate, so then width is the effective width is 2 times the fin, because current flows from the bottom of the fin to top of the fin, that is over the length of the height of the fin, H fin. So our effective width is 2 times the H fin, plus if it is a tri-gate on the top side, so that is covering the whole thing, so that gives your T fin. So this is tri-gate. Yes, this is tri-gate, and if it is double gate, only 2 times H fin minus is whatever the encroachment DW. Next page. So next page. So we know that FinFET was adopted in 2011 by Intel, but this was invented in 1980. So actually, a lot of textbooks, what I have seen, they normally don't have this information that it was invented in 1980. So it was invented by Yutaka Hayashi, so from in Japan. So that is so this patent number. So he submitted his patent on June of 1980. So this patent called MOSFET effect transistors. On the left hand side, you see that this is the FinFET structure. FinFET structure, and on the right hand side, exactly along Z prime. So you see there is a 2D cross section. So that is exactly FinFET. So this was known since from 1980. So he submitted in 1980. So then, but it was first it was published in 1982, and before patent examination, and then after patent examination, it was published in 1987. So it is on public domain from 1982. But a lot of people don't know, because it's a Japanese patent, and I had very hard time to interpret that with a lot of my friends from Japan. So ultimately, the patent was granted in 1993. So it took 13 years to grant this patent. By that time, a lot of people published these double gate MOSFET as well as triple gate MOSFET papers without acknowledging this invention. But anyway, so in my book, I actually detailed this patent in the introduction chapter of my book, coming out in July. So on the next page. So this compares this. So this shows that this project, though it was invented, so this project was undertaken by UC Berkeley under the leadership of Chen Ming Ho. So under this project of government DARPA project on novel fabrication, device architectures, and physics of 25 nanometer FETs for terabit scale electronics. So this was the project under the defense DARPA project, and then this technology was developed at University of California, Berkeley. So during 1997-2001. So, and then it was on the next page, it shows that it was adopted by Intel, or maybe at the bottom of this page, it shows it was adopted by Intel in 2011, and then followed by several other companies like TSMC, Samsung, Global Foundries, and so on. Next page. So, okay, next page, it shows that. So transformation from MOSFETs to FinFETs, MOSFETs to FinFETs is 2011. So Intel announced to adopt FinFETs for sub-22 nanometer microprocessor technologies. And then later, more semiconductor manufacturers like TSMC, Samsung, Global Foundries followed Intel. So, and next page. Next page is just an overview of FinFET process flow. So FinFET, both bulk as well as SY FinFET can be replicated with the flow is almost same. So first part is differences. So this is a bulk FinFET. So first part only difference is you start with bulk wafer. So that is bulk silicon wafer starting material, and then we have to do oil formation because of bulk fin. We have to have a N-well, P-well formation. Then we do fin patterning. So, but this also can be done in two different ways. First, we can do exactly CMOS process, that is oil formation, then we do fin patterning, or we can skip. We can first do fin patterning, and then after do oil formation, then it follows the regular. And SY FinFET, actually, we don't have oil patterning, oil formation. So we start the SY wafer and then do fin patterning and then go follow the process. That process continues is form the dummy gate, then source drain extensions in formation, then source drain formation, all the spacers and everything are there. Then raised source drain formation. Then replacement. First, we are working all this thing with dummy gate. Then we have to do replacement metal gate, and then metal work function engineering, and then contact, and then back end of the process. So this is the basically brief flow of the process. But this is not that simple. In between, these are very complicated. FinFET process is very complex, particularly if you go to bulk FinFET because of the oil formation and followed by fin patterning. So SY is a little bit easier. We'll compare later on. So next page. On next page, we show just a few steps. So we start with, as I mentioned, we start with epitaxial wafer. So this is P plus silicon, or it is epitaxial silicon. So this silicon thickness that defines the fin height. So we select the epitaxial silicon layer so that this is defines the fin height depending on the requirements for design. Then from there we move to just tin oxide, and then I skip a lot of steps. Then we form P-well and N-well process, that implants and all sorts of things, cleaning and everything from the P-well and N-well. And the next page, we show the main how we form the fin. So fin patterning is the most important process in FinFET technology. So in this case, you deposit a stack of layers starting from after the P-well formation, after a stack of layers. So that is we have this pad oxide, which is white. Then we have silicon nitride. Next layer is silicon nitride. Then amorphous carbon, which is called back anti-reflection coating. So after that, so then we do photolithography. Skip some step. We do photolithography and then do patterning. So this gives the photoresist pattern on the right hand side curve of the top figure, top 3D structure. And then after that, we remove the photoresist and then etch with photoresist. We etch the carbon, which is also called so this carbon layer we remove. So we have then this after photoresist and etching, we have only these carbon blocks. So these carbon blocks we have, and then we do spacer deposition. So this is on the right hand side, bottom right hand side figure. So that shows spacer on the top. So this is actually the spacer defined technology for FinFET, or it is also called SADP process. So define fin, we define this, deposit the spacer, and then do spacer etch on the next page. On the next page, we do spacer etch. So we do spacer etch. So that leaves behind oxide spacers, and carbon is in between, right? So carbon is in between. So then on the right hand side, top 3D structure, we have we remove the carbon. So then we have left behind these only the oxide spacers. So these oxide spacers will define our fins. So then we move to the left 3D picture at the bottom. So that actually we do further etch until the edge stop at the pad oxide of that white part. And then so we have this, and then we do further etch down to your at the bottom of the P silicon, epitaxial silicon. So we have this trench. We have this trench, and then we do skip on the next page. We skip some of the steps, and then we have a trench formation. So we have a trench formation, and then after cleaning and removing and etching, so we get this is the silicon fin. So in between there are a lot of process. So this is the silicon fin standing here, and then we have HTI, and then sometimes we have odd number of fins. So this odd number of fins you have to remove. So this is after fin removal. So this is actually on the left hand side we have actually a P well, and on the right hand side we have N well. So that means P well will be formed on the, if you look at the bottom 3D picture, P well will be formed on these 3 pins. NMOS will be formed on the left 3 pins, and PMOS will be formed on the right 3 pins. So on the next page, on the next slide, after the metallization. So metallization is also a very lengthy process, because this gate is not that easy. You have to remove the dummy gate, then you have to etch it. We have a huge trench. Then that trench you have to fill it out, and etching and everything. These are all huge, complex process. So, but anyway, I skipped all those, and then this shows the after formation of source drain. So silicon carbide. These are raised source drain for. So I'm just talking about the middle 3D picture. So 3D picture, middle 3D picture, that is showing the pins. So silicon carbide, that is a dark blue. So that shows raised source drain of NMOS, and the green, that shows the raised source drain for PMOS, which is silicon germanium. That is stretcher also, that puts the stress on PMOS devices. And then on the left hand side, it shows the 2D cross section of the fins just under the gate. Just under the gate, what we show, it's on the left hand side is P well. Then we have the undoped fin. So this is and then we have a there is a little small in this 2D structure. We have a bottom interface layer of oxide. So we use high K dielectric, but high K dielectric, before high K dielectric, we have to use a thin silicon interface layer. So that silicon, thermally grown silicon interface layer. Then we have high K dielectric, and then we have a TIN layer, and then TAN layer. So that consists of, on both sides it is the same. And then so this actually gives your work function engineering for PMOS devices. So work function engineering, so that is TAN layer that is used as work function for PMOS metallization, PMOS metal gate. And then for NMOS, then we have to do another deposition of aluminum, and then let it diffuse to form aluminum nitride for NMOS work function, which is about 4.1 electron volt, and PMOS that forms about 5.6 or 5.7 electron volt. So this is a metal gate effective work function. So next page, so we'll come to the end very soon. So this actually compares. So as I described before, the only difference in bulk and SY FinFETs is starting wafers, and then in bulk FinFETs is complex process flow because it requires N and P oil formation, requires STI formation to isolate neighboring devices, and so challenging to control fin height. So fin height has to be controlled, and there is no H top layer to control fin height. But on the SY devices, it is simple process. Process flow is very simple. No need for oil formation, no need for STI formation. So fin height is very easily controlled because we have STI as the S stop. Any etching that you are doing, it will be stopped at STI. So that is easy to control fin height. So that reduces variability of FinFET devices. But here variabilities will be large because each fin you cannot control, and if you use multiple fins for a device, that means each fin will have variability in height. So as a result, that will contribute more variability in bulk FinFETs. But on the other hand, SY FinFET, bulk FinFETs is easy, and technology is very simple. Simple means complex, but at the same time, it is the same CMOS technology. We can run on the same line, and but bulk FinFET, we have an expensive wafer cost. So there is a lot of debate which one is better, whether we go to expensive wafer cost or you go for simplified or complex process with low cost. So on the next page. So next page is just shows some device characteristics. So it's the high performance devices. So on the left hand side, IV characteristics, transfer characteristics, IDVG, and the right hand side, IDVD characteristics. So these are very high performance devices. This gives the total current. And so we go to the next page. So we'll just overview some conventional transistors also. FinFET has a lot of challenges. I described in my book on chapter 9. So all these things will take a long time to discuss. So let's just overview on the next page some conventional MOSFET devices with advanced channel engineering. So there was one device which is a deeply depleted channel. So this was developed by SuVolta and Fujitsu, and actually this technology is already used in iPhone, starting from iPhone 8. This technology already used. So what is this technology? This is actually undoped channel. So number one that it shows on the left hand side 2D structure. Number one is undoped channel, so that is white, and then number two is the VT adjust, threshold voltage adjust layer, and then number three is actually short channel control layer, and then number four is anti-constant layer. So these are different layers. It's implanted before we implanted, and after that do undoped epitaxial layer, which is one, and then so all these layers may up diffuse, and then so that actually forms the channel. So this is engineered MOSFET devices. So this actually, since it is undoped, it gives lower process variability, and this can be used for ultra low power technology also. That's how it is used in the iPhone, starting from iPhone 8. So on the next page. On next slide, we show another device which is also undoped. So here it is, instead of doing what SuVolta's technology did, so here it is used halo devices. So double halo MOSFET. So what we do is here use about two halos, all the implants, that means halo, and then channel optional threshold voltage implant, then P oil, N oil, all these things were implanted before using a dummy gate like the FinFET process, and then clean up the surface after all the implants except source drain, clean up the surface, and then then deposit the epitaxial layer, undoped epitaxial layer, and then let all the implants from the bottom up diffusion. So that actually forms, you have halo layers from the deep surface, and with this undoped layer on the near the surface. So that actually gives less variability, and then is also ultra low power, and that can be used similar to SuVolta's devices, but it is a little bit better than DDC devices. DDC devices also some issues because of the heavy doping at the bottom. But here it is, halo is heavily doped, not that heavily, but at the same time, it is since it is up diffused. So this is not that heavily doped layer; it is actually graded layer. So that actually has have advantage. So then on the next page, we'll hurry it up a little bit. So on the next page, it shows that how we do the double halo. So this is double halo is first we do one halo, which is around the source drain extension, and then do the neck with the spacer, and then we do second halo with a less doping concentration. So this is heavily doped, this is lightly doped. Second halo. So that actually idea of that is actually covers the leakage from the deep source drain. So these are the two halos. And so if we go on the next page, so this is the concept used for double halo, buried halo for MOSFETs. So buried halo MOSFETs, we use the same concept. Then after that, we use the epitaxial layer, undoped epitaxial layer, so that are used from the structure. So this is even better than the original double halo MOSFETs. So this buried halo is better in that respect. And on next page, we will show some device characteristics in next few minutes. So this is actually the complementary structure that shows NMOS on the left hand side and PMOS on the left hand side. That is the sketch that is used for pattern. And then we go to the next page. Next page shows some process structure. There's some process flow. So on next page.
Hello, Dr. Saha. Your voice is not audible.
Oh, okay. So can you hear me now?
Yeah, now we are able to hear you.
Oh, okay. Actually, I think screen was frozen for a while.
Yeah, please.
So actually, you can go to the next page.
Yeah, please.
Hello, Dr. Saha. Good evening, sir. Can you please share your PPT?
Pardon me?
Hello. Can you
Yeah,
please share your PPT?
we will be sharing this recording videos to you. Please mute yourself. Let him finish the presentation.
Okay, sure.
Okay, sir. We will wait.
Okay. So have the control.
Yeah, Dr. Saha, please proceed. I have changed the slide. Yeah.
Okay. So actually process flow. So this is process flow, just a brief outline. So first, as I mentioned, oil implants. First of all, silicon substrate is doped with oil implants. Optional threshold voltage implant. Multiple halo implants. Halo 1, halo 2, and it will be more than that. And then so shallow halo and the deep halo. So all the implants are done as shown in this 2D structure. And then on the next page, it shows that after all the implants, then we clean up the surface of the wafer, and then we do undoped epitaxial layer deposition. So that epitaxial layer, so this is shows the thickness of the epitaxial layer, and then we have all the implants will up diffuse on the top. So and then but on the surface will be still undoped. And then final fabrication steps below the 2D structure shows you have to do isolation, then gate engineering, and source drain engineering, and then metallization. And then next slide. So this is the final structure. We have seen all the pattern structure in black and white. So this is basically the same structure. And then we can move on the next page. So this shows the IV characteristics, which is nothing new, and it is actually there is no comparison, but still it is much higher than we have a very good control of leakage current, offset leakage current, which is about 10 nm per micron, and then we have a very high performance both NMOS and PMOS. And on next page it shows some process variability. So this is just to check how is the variability is doing, because this is still bulk MOSFET. So if we compare with bulk MOSFET, variability is actually basically we measured by this coefficient AVT. So that coefficient is higher for bulk MOSFET, and actually with this this double halo or buried halo MOSFET is just half of it. So and then next page shows the threshold voltage is controlled. So threshold voltage, we compare with the bulk MOSFET with a standard MOSFET. So for this is a threshold variation, vertical axis, and then channel length on the lateral axis. So it shows that for if it is both W and L is short, that is about below 10 nanometer, we have a V threshold variation is about close to 90 millivolt. And whether and if it is about W is about 200 nanometer, that is very large W, then it comes to about 45 millivolt. On the other hand, if we use buried halo device, then even for 20 nanometer device, still we have is about 45, and then if it's 200 nanometer device, it is about 25. So it's much better threshold, much better variability performance than the bulk FinFET, sorry, bulk MOSFETs. And then on next page shows the curve. Next page shows the variation of ion and on current, that is on current distribution for both N MOSFET and P MOSFET. So this shows the global and local variation. That means outer of these lightly these squares with light. So the outer squares that shows the total variability, global plus local, and then blue that shows actually only global variation, and then Monte Carlo, and then MC local variation only using Monte Carlo that shows the inner those circle. So that is and then the typical and all the corners are also shown. That is at the center TT, typical corner, then fast corner, slow corner, and all the different corners are also shown. So this shows that it is well controlled, and we can actually this is a statistical model plus regular model that is actually coincides very easily. That is, we can use either statistical model or we can use regular model to just model this technology. So then on next page. So then next is summary. So in summary, so I hurried a little bit because I know it is late for you guys. So in summary, silicon device technology and MOSFETs continue to make unprecedented impact on society, leading to internet and enabling smart environments and integrated ecosystem. CMOS technology faced with unsurmountable physical challenges. Some of them we discussed. And then FinFET device technology has been implemented as the alternative technology for high performance VLSI circuits. manufacturing. Channel engineering planar MOSFETs on undoped epitaxial layer also shows great promise for analog RF applications, particularly the technology that I described, buried halo, that is perfect for, and then it is a low leakage, low process variability, and low power. That is great technology. Both SuVolta's technology as well as buried halo, both are low power, low variability, green technology. So with that, next page. With that, thank you very much for this thing late. For my case, my day is just started, so it is good for me. And then, so please stay safe. And then, so if you have any questions, you can send to organizers or send directly to me. So I will answer.
Yeah, thank you, Dr. Saha, for nice presentation. Now we will take few questions which I have already received in the chat window, and if you can answer, that will be good. We know that we are already at 9:40 in India night, but still, because till end people have attended and listened to your presentation, it is better that at least few questions you should take, and remaining we can pass on to room. Yeah,
sure. But people will skip dinner, I think, right? Dinner and then.
Yeah. Yes. So why it has SIGE and SIC? This is the question. First question I can see there.
Okay,
Silicon germanium and silicon carbide. Yeah.
Okay, silicon germanium. Silicon germanium source drain extension. Source drain is used to actually compressive stressor to PMOS channel. So that increases, that stress increases the mobility of a device, mobility of a channel mobility. As a result, it increases the performance of CMOS devices, PMOS devices. Channel devices, performance improvement. And on the other hand, silicon carbide, which is silicon germanium, does not do anything. That stretcher does not help NMOS. So NMOS has to have a stretcher from the top. So that silicon carbide is used for NMOS. So it is on the top also, top of the fin. So that is actually compressive. The other one was compressive stress. This was actually stress from the top. So that's why silicon carbide, which is N-type, N plus type, that is used for NMOS raised source drain.
Okay, thank you. Next question is, which transistor occupies more area, whether MOSFET or FinFET? Request all of you to please mute yourself, otherwise it will be really difficult to.
I didn't quite follow that first part. Which difference? Which transistor is better or what?
No, they are asking which transistor occupies more area, whether MOSFET or FinFET. Area wise, they are asking which MOSFET occupies more.
FinFET has strict requirement, but actually area wise, FinFET is better because FinFET is vertical device, right? But narrow vertical device, and MOSFET is a lateral device. So lateral device, all the spacers and everything, it takes time. So it takes actually the real estate, that means space. So I think space wise, probably the FinFET is better. It's a vertical.
Yeah, thank you. The next question is, how is carbon deposited and etched?
Okay, so carbon is deposited, if I remember, it is by CVD process, chemical vapor deposition process, and or it could be deposited in ALD process also. So I have to look at that. Yeah, I think that carbon, it is called mandrel. So that actually helps the formation of spacers, that is spacer-defined technology. Mandrel means it's a helper. So it is, you can do regular chemical vapor deposition.
Thank you. Next question quickly I will take. What are the problems that a ultra thin body transistor mitigates when compared to a conventional MOSFET?
So as I touched a little bit, that ultra thin body, what happens is, since you have ultra thin body, so gate is closer, you need place closer to the surface. Gate cannot control far away from the surface. Gate only controls, on the smaller devices, gate only controls surface. So if it is far away from the surface, as I was saying, that you need to bring gate closer to the body. So when you take the ultra thin body, so it is closer to the surface. So that's how gate control is improved, and so as a result, you reduce the leakage.
Yeah, so I will take last question. Asking what is second meeting. By the time I'm asking question, people are typing, so it is going up.
Okay.
Okay. Why Intel did not adopt Japanese FinFET implementation?
No, Japan, FinFET actually, Intel everything whatever does, they do much better. They do better. So they never adopted any technology. Even when it was MOSFET, CMOS time, their leakage current was always 2 to 3 orders better than regular industry. So they have a unique way of doing things. So though they took it from UC Berkeley, but at the same time they improved their performance. So they have their lots of people they do work which nobody knows, but their performance is always good. So it is although if you are talking about that original patent which was invented in Japan, so actually it is that is actually flowing indirectly or directly. People are using the same thing, only probably without acknowledgement, because a lot of people did not know. As I mentioned, it is in Japanese. You cannot read it is all in Japanese. You cannot read it. And the first few papers was published in Japanese also.
Okay, again, last question firmly. What is the maximum operation and what is the space radiation immunity devices?
Okay, maximum or minimum frequency operation.
Yeah, maximum frequency.
It is in I don't know the number, but it is in gigahertz range. So FinFET is as good as a silicon MOSFET. So it is in gigahertz range.
Okay, and what about space radiation immunity?
Space radiation immunity, it is the same as silicon devices. So it is a MOSFET. It is a CMOS technology. So it is the same.
Okay, thank you, Dr. Saha. Thank you very much for this. And still, I can see 80 people are there. I will just give a small introduction about you. We because of high tension, from switch over from one room to another room, and then links, I could not do it. So I will read out his bio. Dr. Samar Saha served as the 2016-2017 president of IEEE Electron Device Society (EDS) and is currently serving as the senior past president of EDS. He is an adjunct faculty in the Electrical Engineering Department of Santa Clara University and chief scientist as Prospicient Devices USA. Since 1984, he has worked in various technical and management positions for National Semiconductor, LSI Logic, Texas Instruments, Philips Semiconductor, Silicon Storage Technology, Synopsys, DSM Solutions, Silterra USA, and SuVolta. He has also worked as a faculty member in the Electrical Engineering Department of South Illinois University, Auburn University, University of Nevada, and the University of Colorado. With this brief introduction, I would like to thank all of you for joining us in this very late night, and I am also thankful to Dr. Samar Saha. We wrote him only one mail, and he has been kind enough to accept this. And we got very nice perspective about the future of electronic devices, as well as how we are. I think this presentation was very members, and I can see there are a lot of not members joined it. So thank you very much, sir. And if you want, you give some concluding remarks, and we will close the meeting.
Okay, thank you all. Thank you all for skipping the dinner and then attending this talk.
Thank you, Dr. Saha, and thank you, Puneet.
Yes, sir.
Thank you.
Thank you very much.
Okay, bye.